To our last part here on chemistry and physiology. We'll talk a little bit about pH and what this means for the body itself and what it just means to measure the pH, as pH plays a pivotal role in the body. So pH is essentially just a measure of the acids and bases, and more so it's a measure of the amount of hydrogen ions or hydroxide ions we have within a particular solution that is there. And many different foods that we have different types of pH within them. And so if we were to just go tap water, for the most part, tap water is going to have a relatively neutral pH. So it's going to be at a pH of 7 there. So our pH scale on this side. pH running from 0 to 14, and it's going to relate to the, again, the amount of hydrogen ions or hydroxide ions that we have there within them. And so the more hydroxide ions that we have, the more acidic a substance is going to be. And so therefore the more the pH is going to drop. As we get more hydroxide ions, that pH is going to rise up and it's going to become more basic for different substances that we have. Slightly different picture of the same thing. And so different types of processes. Here we can see that the more acidic a substance is, the more hydrogen ions we're going to have there. The more basic a substance is, the less hydrogen ions that we're going to have. And so we're going to change kind of what's going on there. We're going to have more hydroxide ions within there for those particular substances themselves. So on our pH scale, once again, neutral is 7, and this is where basically pure water is going to be. We'll see that in our own blood. The average pH is about 7.4 or so, so we're slightly on the basic side for things within the body. And depending upon what's going on within our body is going to dictate essentially whether we need to try and lower the pH or try and bring that pH back up. And as we go along through the entire physiology process, we'll start to learn about different systems and different processes that work to get that pH back to a normal process. So acids and bases. And so we have our acids here. Acids, as we put them into a solution, they're going to release hydrogen ions. So that's where we have hydrogen ions more so in that solution that is there for them. Hydrogen ions are oftentimes referred to as proton donors, and so they are protons themselves. They have a single proton within them for those, and so they can be a proton donor. This is where sometimes you may have heard of something like a proton pump inhibitor, and so for alleviating acid reflux and GERD and things like that, those proton pump inhibitors stop those protons from being able to be released on those. And so that hydrogen ion itself, once it loses that electron that it has there, is just a proton. So there's no electron there, there's just a proton within it. And so that's where oftentimes they are referred to as that proton donor that is there. The more acid that we have, and so, or the more acidic a substance is, the more profusely, the more readily it's going to lose those hydrogen ions. And so that the more that those hydrogen ions are going to come off within that particular substance. And so if we add hydrochloric acid to something like water, those hydrogen ions are going to come off and they're going to dissociate, and we're going to have a acidic solution that's there. Bases are, in a sense, kind of the opposite. They're, rather than donating their hydrogen ions or donating their protons, they're going to accept them. So they're going to take them into themselves in a sense. And so they're going to bring those in there. They oftentimes are going to release hydroxide ions. They don't always have to, but they oftentimes will when that occurs. And with that, we then have something here like sodium hydroxide. And so sodium hydroxide is going to dissociate into a sodium ion and then our hydroxide ion. And so we have the two that are there. As we then take our sodium hydroxide and do something like mix it with water, once again, it's going to have those hydroxide ions coming off of it as they start to dissociate within. So within our body, we have these acids and bases, and different foods are bringing things in. Even just simply holding our breath starts to change the pH, or breathing extra changes the pH. And we can get ourselves into situations where we have either acidosis or alkalosis. And so different processes that are going on within the body alter the pH of things that are there. If we do go too far out of that 7.4 average, and so if we get away from that 7.4, things start to go, in a sense, bad within the body itself. And so chemical bonds can start to be broken as we change that pH. Proteins can be altered that are there. Normal cellular functions may not work at a particular pH, and so things like enzymes stop functioning at a lower pH or a higher pH, depending upon where they are. And so this can stop normal cellular functioning that we have, especially when we start to talk about things like even just digestion. That's there. As we start to get below that 7.35 range, we start to get very, very acidotic. And so if we're not able to blow off things like our CO2, and so if we're holding our breath, our pH is going to start to fall. So as CO2 levels go up, pH levels come down. That can get us into a acidotic state within the body itself that is there. And so we're going to need to be able to do something to bring that pH back up. Conversely, if we get into an alkaline state, if we were breathing too quickly, our CO2 levels would start to fall, and that's going to start to bring our pH up. And so both of those are going to start to have us some problems there. Nervous system does not like to function below a pH of 7. Things like muscles, again, being able to contract under a normal situation if the pH starts to go up too high. So we're going to start to have muscle contraction when we didn't necessarily want to have that contraction. So if our pH is starting to go too low, or if our pH is starting to go too high, we don't want that. And so in order to keep our pH kind of going in just a relatively normal process, with kind of the average being there, and so 7.45 being up here, 7.35 being down here, and that middle road being our pH of 7.4, we have buffers and we have buffer systems within the body itself. And so these are chemicals which are going to minimize that change of pH regardless of kind of what's going on. So if we drink something that's very acidic, if we're getting acidic foods into our diet, we don't want our pH to all of a sudden start to plummet. We want to have a relatively smooth process. And so if acidic substances are coming in, we want to try and bring them back up towards that neutral. And that's where buffers come into play within the body itself. And this is going to stabilize the pH. This is going to make it so that we maybe get a little blip in the pH, but no big drastic changes that are there within the body itself. And so that's where the buffers come into play. We have buffers in the blood. And so different substances, as I said, just simply holding your breath or breathing, hyperventilating, can cause pH to start to change relatively quickly. So we need to have buffers within the blood to be able to very quickly make those alterations. Things like even just using muscles to an extent where they're going to become fatigued, that can start to make changes within the pH of the blood as well. So buffers become very important, and this is another one of those things that we'll look at in lab to see how buffers can be used in order to stabilize the pH, and so that we don't see this big change to pH even when we have something that is relatively acidic or basic being added to a solution. And so that's the end of our look into chemistry. We'll look at biochemistry as well in just a little bit.